Light and reflection, the behavior of light as it bounces off things. The Very Large Array, located near Chiraco, New Mexico, consists of 27 radio antennas, each 25 meters in diameter. These antennas detect electromagnetic radiation in the radio and microwave regions of the spectrum. The dish of a radio telescope reflects the radio waves and focuses the rays at the receiver poised above the dish. It will actually be the focal point, that point above the dish where the light rays converge. Chapter illustration, the Very Large Array, VLA, is part of a project called National Radio Astronomy Observatory, NRAO. Radio astronomy is used to produce images of celestial bodies. A number of celestial objects emit more strongly at radio wavelengths than at those of visible light. The VLA is used to study both distant celestial objects as well as our sun. Chapter 13 Overview, Characteristics of Light, Section 1 identifies the components of the electromagnetic spectrum, relates their frequency and wavelength to the speed of light, and introduces the relationship between brightness and distance for a light source. Flat mirrors applies the laws of reflection to plane mirrors and uses ray diagrams to determine image location. Section 3, Curved Mirrors, shows how image location and magnification are calculated for concave and convex mirrors, uses ray diagrams to confirm calculated results, and explains spherical aberration. Section 4, Color and Polarization, investigates additive and subtractive colors and explores the phenomenon of polarization. The chapter preview, divided into 4 sections. The first section is one subsection, electromagnetic waves. That section is called Characteristics of Light. Section 2, Flat Mirrors, is broken into reflection of light and flat mirrors. The Section 3, Curved Mirrors, is broken into concave spherical mirrors, convex spherical mirrors, and parabolic mirrors. And Section 4, Color and Polarization, is divided into color and polarization of light waves. Knowledge to review. You should go back and review waves transport energy. They can be transverse or longitudinal. Waves have amplitude, frequency, wavelength, and velocity. Items to probe. The ability to describe spatial relationships in geometric terms. Make sure students understand terms such as perpendicular and parallel, and can solve equations of the form 1 over a plus 1 over b equals 1 over c, where you're actually going to solve for c. Take the reciprocal of the answer to 1 over b plus 1 over a. Additional items to probe. Preconceptions about light. Ask students to describe the path of sound waves when we hear something and the path of light rays when we see an object. What to expect. In this chapter, you will learn about the characteristics of light and other forms of electromagnetic radiation. You will learn how flat and curved mirrors can be used to reflect light and create real and virtual images of objects. Why it matters. Mirrors have many applications both for scientists and in everyday life. For example, a reflector telescope uses 2 mirrors to gather, focus, and reflect light into the eyepiece. The reflector telescope remains one of the most popular designs used by amateur astronomers, even though it was invented over 300 years ago. Section 1, Characteristics of Light. 4 objectives. 1, identify the components of the electromagnetic radiation spectrum. 2, calculate the frequency or wavelength of electromagnetic radiation. 3, recognize that light has a finite speed. Last, 4, describe how the brightness of a light source is affected by distance. Electromagnetic waves. When people think of light, they think of the light that they can see. Some examples include the bright white light that is produced by a light bulb or the sun. However, there is more to light than these examples. When you hold a piece of green glass or plastic in front of a source of white light, you see green light pass through. This phenomenon is also true for other colors. What your eyes recognize as white light is actually light that can be separated into 6 elementary colors of the visible spectrum. Actually 7, but we won't argue with them. Red, orange, yellow, green, blue, indigo, and violet. Figure 1, a prism separates light into its component colors, Roy, G, Biv. Indigo is actually very dark. If you examine a glass prism, such as the one shown in Figure 1, or any thick triangular shaped piece of glass, you will find the sunlight passes through the glass and emerges as a rainbow-like band of colors. The spectrum includes more than visible light. Not all light is visible to the human eye. If you were to use certain types of photographic film to examine the light dispersed through a prism, you would find that the film records a much wider spectrum than the one you see. A variety of forms of radiation, including X-rays, microwaves, and radio waves, have many of the same properties as visible light. The reason is that they are all examples of electromagnetic waves. Electromagnetic waves, the waves that consist of oscillating electric and magnetic fields, which radiate outward from the source at the speed of light. Light has been described as a particle, as a wave, and even as a combination of the two. Although the current model incorporates aspects of both particle and wave theories, the wave model is best suited for an introductory discussion of light, and it is the one that will be used in this section. We will study the wave-particle duality of light later on. An electromagnetic wave consists of electric and magnetic field waves at right angles to each other. Electromagnetic waves vary depending on frequency and wavelength. In classical electromagnetic wave theory, light is considered to be a wave composed of oscillating electric and magnetic fields. These fields are perpendicular to the direction in which the wave moves, as shown in Figure 2. Therefore, electromagnetic waves are transverse waves. The electric and magnetic fields are also at right angles to each other. Electromagnetic waves are distinguished by their different frequencies and wavelengths. In visible light, these differences in frequency and wavelength account for different colors. The difference in frequencies and wavelengths also distinguishes visible light from invisible electromagnetic radiation, such as X-rays, microwaves, infrared, ultraviolet, etc. Here's a table, Table 1, the electromagnetic spectrum. It starts with radio waves, microwaves, infrared waves. This is important information for you to look at. Visible light, ultraviolet light. Certain amount of memorization is good for you. Learning takes place at the beginning. Memorization is the beginning. Now we round off our list with X-rays and gamma rays. And each type, each classification is also not only given the range but the application. Types of electromagnetic waves are listed in Table 1. Note the wide range of wavelengths and frequencies. Although specific ranges are indicated in the table, the electromagnetic spectrum is, in reality, continuous. There is no sharp division between one kind of wave and the next. Some types of waves even have overlapping ranges. All electromagnetic waves move at the speed of light. All forms of electromagnetic radiation travel at a single high speed in a vacuum. Early experimental attempts to determine the speed of light failed because this speed is so great. As experimental techniques improved, especially during the 19th and early 20th centuries, the speed of light was determined with increasing accuracy and precision. By the mid 20th century, the experimental error was less than 0.001%. The currently accepted value for light traveling in a vacuum is essentially 3 times 10 to the 8th meters per second. Light travels slightly slower in air with only a few significant figures difference. You can see those values yourself. They're very, very close. But indeed, they're different. So change the air, and you'll change the speed of light. For calculations in this book, the value used for both situations will be 3 times 10 to the 8th meters per second. The relationship between frequency, wavelength, and speed described in the chapter on vibrations and waves also holds true for light waves. So it's going to be the wave speed equation will be C equals F lambda, where the speed of light equals frequency times wavelength. Sample A, sample problem A, electromagnetic waves. The AM radio band extends from 5.4 times 10 to the 5th hertz to 1.7 times 10 to the 6th hertz. What are the longest and shortest wavelengths in this frequency range? Here's what's given. The speed of light note is 3 times 10 to the 8th meters per second. The unknowns are going to be wavelength 1 and wavelength 2 corresponding to F1 and F2. So we're going to have to pick out the right formula, and then we're going to rearrange the formula and calculate. Use the wave speed equation. So here's the wave speed equation. You're going to plug in frequency, and you're going to calculate wavelength. And wavelength 1, wavelength 2, we're calculating. And you're going to plug in the values that are given, as well as the speed of light, which is also given. And it's going to be 560 meters. And the next one will be 180 meters. Notice the inverse relationship between frequency and wavelength. Gamma ray bursters are objects in the universe that emit pulses of gamma rays with high energies. The frequency of the most energetic bursts has been measured at around 3 times 10 to the 21st hertz. What is the wavelength of these gamma rays? So if it's a very large frequency, what does that say about what the wavelength is going to be? And the relationship between wavelength and frequency. That's a pattern that should become obvious to you. So you can see that it's very small, 1 times 10 to the negative 13th meter. And so that's going to be very small. And here's the next one. What is the wavelength range for the FM radio band? And you're going to have F1 and F2, the speed of light. You're going to plug in the values, C over frequency. The first one's going to be 3.4 meters, and the next one will be 2.78 meters. That's something that's not bad. That's kind of real. Shortwave radio is broadcast between 3.50 and 29.7 megahertz. To what range of wavelengths does this correspond? Why do you suppose this part of the spectrum is called shortwave radio? Well, here's the equation. Lambda equals C over F. I'm going to plug in and then solve. 85.7 meters is the first frequency. And then notice I changed the megahertz to just hertz. That's important. And then 10.1 meters. The wavelengths are shorter than those of AM radio band. What is the frequency of an electromagnetic wave if it has a wavelength of 1 kilometer? So a very, very long wavelength. It's going to probably have what kind of frequency? So make sure you change it from kilometers to meters, and you'll get 3 times 10 to the 5th hertz. The portion of the visible spectrum that appears brightest to the human eye is around 560 nanometers in wavelength, which corresponds to yellow-green or really chartreuse. What is the frequency of the 560 nanometer light? Here's the equation. Make sure you change it from nanometers to meters and plug in, and you get 5.4 times 10 to the 14th hertz. What is the frequency of highly energetic ultraviolet radiation that has a wavelength of 125 nanometers? So remember to change it to meters. So it's going to be 125 times 10 to the 9th. So it'll be times 10 to the 7th. 1.25 times 10 to the 7th. Just move your decimal point over. And again, change it to meters. Plug in. Don't forget your speed of light in meters. And it's 2.4 times 10 to the 15th hertz. According to Wiggins' principle, a wave front can be divided into point sources. The line tangent to the wavelets from these sources marks the wave front's new position. And what we'll do is we'll look at an example in the ocean as the waves come into shore. Waves can be approximated as rays. Consider an ocean wave coming towards the shore. The broad crest of the wave that is perpendicular to the wave's motion consists of a line of water particles. Similarly, another line of water particles forms a low-lying trough in the wave, and still another line of particles forms the crest of the second wave. In any type of wave, these lines of particles are called wave fronts. All the points on the wave front of a plane wave can be treated as point sources. That is, coming from a source of negligible size. A few of these points are shown on the initial wave front in Figure 3. Each of these point sources produces a circular or spherical secondary wave or wavelet. The radii of these wavelets are indicated by the blue arrows in Figure 3. The line that is tangent to each of these wavelets at some later time determines the new position of the initial wavefront, the new wavefront in Figure 3. This approach to analyzing waves is called Wiggins Principle, named after the physicist Christian Huygens, who developed it. Wiggins' principle can be used to derive the properties of any wave, including light, that interacts with matter. But the same results can be obtained by treating the propagating wave as a straight line perpendicular to the wave front. This line is called a ray, and this simplification is called the ray approximation. Look back on Figure 3 and see if what is written here makes sense with what is there. Illuminance decreases as the square of the distance from the source. You have probably noticed that it is easier to read a book beside a lamp using a 100-watt bulb than using a 25-watt bulb. It is also easier to read nearer to a lamp than farther from the lamp. These experiences suggest that the intensity of light depends on both the amount of light energy emitted from a source and the distance from the light source. Light bulbs are rated by their power input, measured in watts, and their light output. The rate at which light is emitted from a source is called the luminous flux and is measured in lumens, Lm. Luminous flux is a measure of power output, but is weighted to take into account the response of the human eye to light. Figure 4, less light falls on each unit square as the distance from the source increases. That's Figure 4. The idea of luminous flux helps us understand why the illumination on a book page is reduced as you move away from the light source. Imagine spherical surfaces of different sizes with a point source at the center of the sphere, as shown in Figure 4. A point source of light provides light equally in all directions. The principle of conservation of energy tells us that the luminous flux is the same on each sphere. However, the luminous flux divided by the area of the surface, which is called the illuminance, and it's measured in lumens per square meter, or lux, decreases as the radius squared when you move away from a light source. Identify which portions of the electromagnetic spectrum are used in each of the devices listed. A microwave oven, microwaves of course, a television set, a single lens reflex camera, and let's see. So you want to identify the portion of the electromagnetic radiation spectrum. So obviously A is going to be microwave. What's television going to be? Radio waves and visible light, pretty good, and then visible light for the camera. 2. If an electromagnetic wave has a frequency of 7.57 times 10 to the 14th hertz, what is its wavelength? To what part of the spectrum does this wavelength belong? So again, what you're going to want to do is you're going to want to break out your equations, write down the data. You have a frequency and you're calculating wavelength. You know what the speed of light is. You can either memorize it or write it down from a source. And there it is. Everything's plugged in, and you get 3.96 times 10 to the negative 7th meter. Galileo performed an experiment to measure the speed of light by timing how long it took light to travel from a lamp he was holding to an assistant about 1.5 kilometers away and back again. Why was Galileo unable to conclude that light had a finite speed? The distance wasn't probably very far. We tested it on the moon. When we landed on the moon, we put mirrors up, and now we can test it. The speed of light is too great to be measured over such a short distance. The time of travel for the light in Galileo's experiment was about 1 times 10 to the negative 5th seconds. We just didn't have the instrumentation back there to make such close approximations to that speed, that amount of time, that little amount of time. So it was fairly difficult. Now the next question, I'm going to give you the answer and the question. How bright would the sun appear to an observer on Earth if the sun were 4 times farther from the Earth than it actually is? Express your answer as a fraction of the sun's brightness on the surface. Well, it would be 1 over 16 because it's 1 over distance squared is the relationship. Section 2, flat mirrors. Distinguish between specular and diffuse reflection of light. Apply the law of reflection for flat mirrors and describe the nature of images formed by flat mirrors. Suppose you have just had your hair cut and you want to know what the back of your head looks like. You can do this seemingly impossible task by using 2 mirrors to direct light from behind your head to your eyes. Redirecting light with mirrors reveals a basic property of light's interaction with matter. Light traveling through a uniform substance, whether it is air, water, or a vacuum, always travels in a straight line. However, when the light encounters a different substance, its path will change. If a material is opaque to the light, such as the dark or highly polished surface of a wood table, the light will not pass into the table more than a few wavelengths. Part of the light is absorbed and the rest of it is deflected at the surface. Figure 5 shows mirrors reflect nearly all incoming light, so the multiple images of an object between 2 mirrors are easily formed. And you'd actually have to kind of curve it in order to kind of get it to do that. Otherwise, your head would be in the way. This change in the direction of light is called reflection. Reflection, the change in direction of an electromagnetic wave at a surface that causes it to move away from the surface. All substances absorb at least some incoming light and reflects the rest. A good mirror can reflect about 90% of the incident light, but no surface is a perfect reflector. Notice in figure 5 that the images of the person get successively darker. The texture of the surface affects how it reflects light. The manner in which light is reflected from a surface depends on the surface's smoothness. Diffusely reflected light is reflected in many directions, A, whereas specularly reflected light is reflected in the same forward direction. Figure 6. Point out that the incident light rays are parallel. Incident light rays are parallel. Why are the reflected rays from the surface in A not parallel? You want to put this on pause and go back and look at the example. Because the surface in A has irregularities. It forms a different angle with the incident ray at each point. Light that is reflected from a rough textured surface, such as paper, cloth, or unpolished wood, is reflected in many different directions as shown in figure 6a. This type of reflection is called diffuse reflection. Diffuse reflection will be discussed further in section 4. Light reflected from smooth, shiny surfaces, such as a mirror or water in a pond, is reflected in only one direction, as shown in figure 6b. This type of reflection is called specular reflection. A surface is considered smooth if its surface variations are small compared with the wavelength of the incoming light. For our discussion, reflection will be used to mean only specular reflection. All substances absorb at least some incoming light and reflect the rest. A good mirror can reflect up to 90% of the incident light, but no surface is a perfect reflector. Notice in figure 5 that the images of the person get successively darker. The texture of the surface affects how it reflects light. The manner in which light is reflected from a surface depends on the surface's smoothness. Incoming and reflected angles are equal. You probably have noticed that when incoming rays of light strike a smooth reflecting surface, such as a polished table or mirror, at an angle close to the surface, the reflected rays are also close to the surface. When the incoming rays are high above the reflecting surface, the reflected rays are also high above the surface. Figure 7, the symmetry of reflected light A is described by the law of reflection, which states that the angles of the incoming and reflected rays are equal, as in B. Figure 6, visual strategy. In the photo, the light from the flashlight strikes the surface. So look at figure 6, and you'll see that it strikes the surface. And look and see if you can approximate whether or not the angle of incident and reflection are similar. Why is there a bright spot where it strikes the surface? Why is there a bright spot? Okay, look at the bright spot. Ask yourself, why is the bright spot there? Curious. As they say when the plot thickens. Light is scattered off the imperfect or dirty surface. Below the light spot, there seems to be rays at the lower left and lower right. Now, given that answer, look back again at figure 6. What causes these rays? What causes these rays? We are seeing reflections off the mirror surface of the incident and reflected beams above. Just as simple as that. It was not a trick question. An example of this similarity between incoming and reflected rays is shown in figure 7a. If a straight line is drawn perpendicular to the reflecting surface at the point where the incoming ray strikes the surface, the angle of incidence and the angle of reflection can be defined with respect to the line. Angle of reflection, the angle formed by the light perpendicular to the surface and the direction in which the reflected ray moves. Angle of incidence, the angle between a ray and that strikes a surface and the line perpendicular to the surface at the point of contact. Careful measurements of the incident and reflected angles, theta and theta prime, respectively, reveal that the angles are equal as illustrated in figure 7b. Theta equals theta prime. Angle of incoming light ray, angle of reflected light ray. The light perpendicular to the reflecting surface is referred to as the normal to the surface. It therefore follows that the angle between the incoming ray and the surface equals 90 minus theta, and the angle between the reflected ray and the surface equals 90 minus theta prime. Flat mirrors. The simplest mirror is the flat mirror. If an object, such as a pencil, is placed at a distance in front of a flat mirror and light is bounced off the pencil, light rays will spread out from the pencil and reflect from the mirror's surface. To an observer looking at the mirror, these rays appear to come from a location on the other side of the mirror. As a convention, an object's image is said to be at this location behind the mirror because the light appears to come from that point. The relationship between the object distance from the mirror, which is represented as P, and the image distance, which is represented as Q, is such that the object and image distances are equal. Similarly, the image of the object is the same size as the object. The position and size of the virtual image that forms in a flat mirror, A, can be predicted by constructing a ray diagram, B. This is figure 8. The image formed by rays that appear to come from the image point behind the mirror, but never really do, is called a virtual image, as shown in figure 8a. A flat mirror always forms a virtual image, which always appears as if it is behind the surface of the mirror. For this reason, a virtual image can never be displayed on a physical surface. Image location can be predicted with ray diagrams. Ray diagrams, such as the one shown in figure 8b, are drawings that use simple geometry to locate an image formed by a mirror. Suppose you want to make a ray diagram for a pencil placed in front of a flat mirror. First, sketch the situation. We will be doing many of these diagrams in the next 2 chapters. Draw the location and arrangement of the mirror and the position of the pencil with respect to the mirror. Construct the drawing so that the object and the image distances P and Q respectively are proportional to their actual sizes. To simplify matters, we will consider only the tip of the pencil. To pinpoint the location of the pencil tip's image, draw 2 rays on your diagram. Draw the first ray from the pencil tip perpendicular to the mirror's surface. Because this ray makes an angle of 0 degrees with the line perpendicular or normal to the mirror, the angle of reflection also equals 0 degrees, causing the ray to reflect back on itself. In figure 8b, this ray is denoted by the number 1 and is shown with arrows pointing in both directions because the incident ray reflects back on itself. Draw the second ray from the tip of the pencil to the mirror, but this time place the ray at an angle that is not perpendicular to the surface of the mirror. The second ray is denoted in figure 8b by the number 2. Then draw the reflected ray, keeping in mind that it will reflect away from the surface of the mirror at an angle theta equal to the angle of incidence theta prime. Next, trace both reflected rays back to the point from which they appear to have originated, that is, behind the mirror. Use dotted lines when drawing these rays that appear to emerge from behind the mirror to distinguish them from the actual rays, the solid lines in front of the mirror. The point at which these dotted lines meet is the image point, which in this case is where the image of the pencil's tip forms. By continuing this process for all of the other parts of the pencil, you can locate the complete virtual image of the pencil. Note that the pencil's image appears as far behind the mirror as the pencil is in front of the mirror, P equals Q. Likewise, the object's height h equals the image height h prime. Figure 9, the front of the object becomes the back of the image. This ray tracing procedure will work for any object placed in front of a flat mirror. By selecting a single point on the object, usually its uppermost tip or edge, you can use ray tracing to locate the same point on the image. The rest of the image can be added once the image point and image distance have been determined. The image formed by the flat mirror appears reversed to an observer in front of the mirror. You can easily observe this effect by placing a piece of writing paper in front of the mirror, as shown in figure 9. In the mirror, each of the letters is reversed. You may also notice that the angle the word and its reflection make with respect to the mirror is the same. Let's do some section review. Which of the following are examples of specular reflection and which are examples of diffuse reflection? Reflection of light from the surface of a lake on a calm day. What would that be? That would be specular. Reflection of light from a plastic bag. That would be diffuse. Reflection of light from the lens of an eyeglass. That would be specular. And reflection of light from a carpet. That would be diffuse. Suppose you are holding a flat mirror and standing at the center of a giant clock face built into the floor. Someone standing at 12 o'clock shines a beam of light towards you, and you want to use the mirror to reflect the beam towards an observer standing at 5 o'clock. What should the angle of incidence be to achieve this? What should the angle of reflection be? Make your drawing, see what happens. The normal to the surface of the mirror is halfway between 12 o'clock and 5 o'clock. So theta equals 1/2 5 times 360 over 12, which equals 75 degrees. That's the prime and the theta and theta prime. Some department store windows are slanted inward at the bottom. This is to decrease the glare from brightly illuminated buildings across the street, which would make it difficult for shoppers to see the displays inside and near the bottom of the window. Sketch a light ray reflecting from such a window to show how this technique works. Diagrams will vary. Verify that the rays' angles of incidence equals the angles of reflection in the student's drawings. The photograph in Figure 5 shows multiple images that were created by multiple reflections between two flat mirrors. What conclusion can you make about the relative orientation of the mirrors? Explain your answer. The light must be reflected from one mirror to the other in order to form images of images. Therefore, the mirrors must be exactly or very nearly parallel to each other with their mirror surfaces facing each other. They're going to be a little bit of an off slant because that's why you can actually see the image going on and on and on. If one wall of a room consists of a large flat mirror, how much larger will the room appear to be? Explain your answer. It will seem twice as large because the object distance, the distance between the mirror and any point in the room including the back wall, equals the image distance. Why does a flat mirror appear to reverse the person looking into a mirror left to right, but not up and down? An object facing the mirror produces an image that faces the object, and the front of the object corresponds to the back of the image. It appears as if the image is an object located behind the mirror, that is, left, right, reversed. Section 3. Calculate distances and focal lengths using the mirror equation for concave and convex spherical mirrors. 2. Draw ray diagrams to find the image distance and magnification for concave and convex spherical mirrors. Distinguish between real and virtual images. Describe how parabolic mirrors differ from spherical mirrors. Figure 10. Curved mirrors can be used to form images that are larger in A or smaller in B than the object. Concave spherical mirrors. Small circular mirrors, such as those used on dressing tables, may appear at first glance to be the same as flat mirrors. However, the images they form differ from those formed by flat mirrors. The images for objects close to the mirror are larger than the object, as shown in Figure 10a, whereas the images of objects far from the mirror are smaller and upside down, as shown in Figure 10b. Images such as these are characteristic of curved mirrors. The image in 10a is a virtual image, like those created by flat mirrors. In contrast, the image in Figure 10b is a real image. Concave mirrors can be used to form real images. One basic type of curved mirror is a spherical mirror. A spherical mirror, as its name implies, has the shape of part of a spherical surface. A spherical mirror with light reflecting from its silvered concave surface, that is the inner surface of the sphere, is called a concave spherical mirror. Concave spherical mirror, a mirror whose reflecting surface is a segment of the inside of a sphere. Concave mirrors are used whenever a magnified image of an object is needed, as in the case of a dressing table mirror, or oftentimes women use them in compacts to apply makeup. One factor that determines where the image will appear in a concave spherical mirror and how large the image will be is the radius of curvature, or capital R, of the mirror. The radius of curvature is the same as the radius of the spherical shell of which the mirror is a part of. R, capital R, is therefore the distance from the mirror's surface to the center of curvature C. A, the rays of an object, such as a light bulb, converge to form a real image in front of a concave mirror. B, in this laboratory setup, the real image of a light bulb filament appears on a glass plate in front of a concave mirror. Figure 11, visual strategy. This image shows a real image of a light bulb on a glass plate. The bulb itself is off to the left, too far away to fit on the photo frame. There is actually an image of the entire bulb on the plate, but only the image of the filament is bright enough to be seen in the photograph. What represents the size of the object? What represents the size of the object? Well, it'll be h. The image size will be h prime. What represents its distance from the mirror? The object's distance from the mirror. That will be p, as in p's and q's. What represents the size of the image? That will be h prime. H prime. What represents the image's distance from C? What will represent the distance from C? R minus Q. So R is the radius of curvature, and then minus Q. What does F refer to? That's the focal length. The length, the distance from the focal point to the mirror, the focal points. The focal points. Imagine a light bulb placed upright at a distance P from a concave spherical mirror, as shown in figure 11A. The base of the bulb is along the mirror's principal axis, which is the line that extends infinitely from the center of the mirror's surface through the center of curvature C. Light rays diverge from the light bulb, reflect from the mirror's surface, and converge at some distance Q in front of the mirror. Because the light rays reflected by the mirror actually pass through the image point, which in this case is below the principal axis, the image forms in front of the mirror. If you place a piece of paper at the image point, you will see on the paper a sharp and clear image of the light bulb. As you move the paper in either direction away from the image point, the rays diverge and the image becomes unfocused. An image of this type is called a real image. A real image, an image that is formed by the intersection of light rays. A real image can be projected on a screen. Unlike the virtual images that appear behind a flat mirror, real images can be displayed on a surface, like the images on a movie screen. Figure 11B shows a real image of a light bulb filament on a glass plate in front of a concave mirror. This light bulb itself is outside the photograph to the left. Images created by spherical mirrors suffer from spherical aberration. As you draw ray diagrams, you may notice that certain rays do not exactly intersect at the image point. This phenomenon is particularly noticeable for rays that are far from the principal axis and for mirrors with a small radius of curvature. This situation, called spherical aberration, also occurs with real light rays and real spherical mirrors and will be discussed further at the end of this section when we introduce parabolic mirrors. In the next pages of this section, you will learn about the mirror equation and ray diagrams. Both of these concepts are valid only for paraxial rays, but they do provide quite useful approximations. Paraxial rays are those rays that are very near the principal axis of the mirror. We will assume that all of the rays used in our drawings and calculations with spherical mirrors are paraxial, even though they may not appear to be so in all of the diagrams accompanying the text. Image location can be predicted with the mirror equation. By looking at figure 11a, you can see that object distance, image distance, and radius of curvature are interdependent. If the object distance and radius of curvature and the mirror are known, you can predict where the image will appear. Alternatively, the radius of curvature of a mirror can be determined if you know where the image appears for a given object distance. The following equation relates object distance, P, image distance, Q, and the radius of curvature, R, is called the mirror equation. 1 over P plus 1 over Q equals 2 over R. It's called the mirror equation. Figure 12, light rays that are parallel converge at a single point A, which can be represented in a diagram B when the rays A are assumed to be from a distant object where P is close to infinity. If the light bulb is placed very far from the mirror, the object distance P is great enough compared with R that 1 over P is almost 0. In this case, Q is almost R over 2. So the image forms about halfway between the center of curvature and the center of the mirror surface. The image point, as shown in figure 12a and b, is in this special case called the focal point of the mirror and is denoted by the capital letter F. Because the light rays are reversible, the reflected rays from a light source at the focal point will emerge parallel to each other and will not form an image. For light emerging from a source very far from a mirror, the light rays are essentially parallel to each other. In this case, an image forms at the focal point F, and the image distance is called the focal length, denoted by the lowercase f. For a spherical mirror, the focal length is equal to half the radius of curvature of the mirror. The mirror equation can therefore be expressed in terms of the focal length. The mirror equation is 1 over P plus 1 over Q equals 1 over F. 1 over the object plus 1 over the image equals 1 over the focal length. A set of sign conventions for the three variables must be established for use with the mirror equation. The region in which light rays reflect and form real images is called the front side of the mirror. The other side, where light rays do not exist and where virtual images are formed, is called the back side of the mirror. Object and image distances have a positive sign when measured from the center of the mirror to any point on the mirror's front side. Distances for images that form on the back side of the mirror always have a negative sign. Because the mirrored surface is on the front side of the concave mirror, its focal length always has a positive sign. The object and image heights are positive when both are above the principal axis and negative when either is below. Magnification relates image and object sizes. Unlike flat mirrors, curved mirrors form images that are not the same size as the object. The measure of how large or small the object is with respect to the original object size is called the magnification of the image. If you know where an object's image will form for a given object distance, you can determine the magnification of the image. Magnification M is defined as the ratio of the height of the bulb's image to the bulb's actual height. M also equals the negative of the ratio of the image distance to the object's distance. If an image is smaller than the object, the magnitude of its magnification is less than 1. If the image is larger than the object, the magnitude of its magnification is greater than 1. Magnification is a unitless quantity. The term magnification sometimes leads students to think that the image is larger than the object. Use a numerical example to show that this is not always the case. Ask students to calculate the image height of a 8 centimeter object when P equals 12 centimeters, Q equals 3 centimeters, and the answer will be negative 2 centimeters. It will be smaller and upside down or inverted. For an image in front of the mirror, M is negative and the image is upside down or inverted with respect to the object. When the image is behind the mirror, M is positive and the image is upright with respect to the object. The conventions for magnification are listed below here. Table 2. If it's upright and virtual, it's positive. If it's inverted, real, it's negative. Equation for magnification. M equals H prime over H, which equals negative the quotient Q over P. Magnification equals image height over object height, which equals negative the image distance over the object distance. Ray diagrams can be used for concave spherical mirrors. Ray diagrams are useful for checking values calculated from the mirror and magnification equations. The techniques for ray diagrams that were used to locate the image for an object in front of a flat mirror can also be used for concave spherical mirrors. When drawing ray diagrams for concave mirrors, follow the basic procedure for a flat mirror, but also measure all distances along the principal axis and mark the center of curvature C and the focal point F. As with a flat mirror, draw the diagram to scale. For instance, if the object distance is 50 centimeters, you can draw the object distance as 5 centimeters. For spherical mirrors, 3 reference rays are used to find the image point. The intersection of any 2 rays locates the image. The third ray should intersect at the same point and can be used to check the diagram. These reference rays are described in Table 3 below. Study them carefully. You need to literally memorize these ray diagrams in order to make your work a little bit easier to do. Here are your ray diagrams. There's going to be 6 of them. Here's the first 2. Study them carefully. I'm not going to read off the table, but you need to study them and to have them make sense to you, perfect sense. And we will go over them in class, but it's vital that you literally memorize these and you can do them on your own. And here's 5 and 6. Study them carefully. The entire section is going to be based on these diagrams. Point out that from all the possible rays coming from the tip of the pencil, these 3 rays are selected because they are reflected according to the simple rules listed in Table 3. Make sure that students understand the application of these rules in the 3 diagrams. Now, when we do the next chapter, we'll look at lenses, but the same idea of drawing ray diagrams. The image distance in the diagram should agree with the value for Q calculated from the mirror equation. However, the image distance may differ because the inaccuracies that arise from drawing the ray diagrams at a reduced scale and far from the principal axis. Ray diagrams should therefore be used to obtain approximate values only. They should not be relied on for the best quantitative results. Concave mirrors can produce both real and virtual images. When an object is moved towards a concave spherical mirror, its image changes, as shown in Table 4 on the next page. If the object is very far from the mirror, the light rays converge very near the focal point F of the mirror and form an image there. For objects at a finite distance greater than the radius of curvature C, the image is real, smaller than the object, inverted, and located between C and F. When the object is at C, the image is real, located at C, and inverted. For an object at C, the image is the same size as the object. If the object is located between C and F, the image will be real, inverted, larger than the object, and located outside of C. When the object is at the focal point, no image is formed. When the object lies between F and the mirror surface, the image forms again, but now it becomes virtual, upright, and larger. A concave spherical mirror has a focal length of 10 centimeters. Locate the image of a pencil that is placed upright 30 centimeters from the mirror. Find the magnification of the image. Draw a ray diagram to confirm your answer. Now, these are the rules. I'm going to take time to read the problem, but then the solution is going to be very fast-paced. And you can always put things on pause if you don't understand a point made. 1. Determine the sign and magnitude of the focal length and object size. Focal length and object size. Here's the data. Your focal length is plus 10 centimeters, and the P, the object's distance from the mirror, is 30 centimeters. The mirror is concave, so F is positive. The object is in front of the mirror, so P is positive. Draw a ray diagram using the rules given in Table 3. There's the ray diagram. Study that carefully. Notice F, C, and which one is the object and which one is the image. Use the mirror equation to relate the object and image distances to the focal length. There's the mirror equation, and we want to plug in some values. Use the magnification equation in terms of object and image distances. There's going to be the magnification equation. And what else? Rearrange the equation to isolate the image distance and calculate. So the image distance will be Q. Subtract the reciprocal of the object distance from the reciprocal of the focal length to obtain an expression for the unknown image distance. All right? As they say, when the plot is about to thicken, the plot is about to thicken. So here we have the rearranged mirror equation calculating Q. Substitute the values for F and P into the mirror equation and the magnification equation to find the image distance and magnification. So now we want to list the givens. And there's the givens as listed before. And we're just going to plow through this. Plug in. And I don't, the book takes a long time to calculate Q by finding what 1 over 10 is and what 1 over 30 is, etc. We have calculators. Just plug into your calculator. It's as easy as that. And the magnification is negative 0.50. Evaluate your answer in terms of the image, location, and size. Now we're going to evaluate. The image appears between the focal point, 10 centimeters, and the center of curvature, 20 centimeters, as confirmed by the ray diagram. The image is smaller than the object and inverted, as is also confirmed by the ray diagram. The image is therefore real. And there's the interpretation of the ray diagram. Study it carefully. Put it on pause if necessary. Find the image distance and magnification of the mirror in the sample problem when the object distance is 10 centimeters and 5 centimeters. Are the images real or virtual? Are the images inverted or upright? Draw a ray diagram for each case to confirm your results. So you want to gather together your equations and your information. There's P1, P2, and F. And there's the equation to calculate Q1. And that's going to be 0. First one. So no image, infinite Q. No image, infinite Q. Now let's do Q2. And it'll be 1/10 over 1/5. And it'll be negative 10. And so it'll be negative 10 centimeters. So that's going to be Q2. Now let's do M. So we have Q1 is infinite. So we're not going to have any image. So M is 2. So that's virtual and upright. And now let's review. There's P1, P2. And there's F is 10. Just gathering together all the facts. Q1 equals 0. Q2 equals negative 10. Upright image. Virtual. And M is plus 2.00. And there is the diagram for the first one. It's because it's at its focal point, there's no image. No image. And then the next one will have a virtual image. Virtual and upright. Just like a makeup mirror. Same exact thing. Same idea. All right. That was good. Now I'm going to do the next one the same way. Just run right through it. Practice B, imaging with concave mirrors number 2. A concave shaving mirror has a focal length of 33 centimeters. Calculate the image position of a cologne bottle placed in front of the mirror at a distance of 93 centimeters. Calculate the magnification of the image. Is the image real or virtual? Is the image inverted or upright? Draw a ray diagram to show where the image forms and how large it is with respect to the object. So here is the givens, the focal length and the distance the object is from the mirror. Here's the equation we're going to use. We're going to calculate Q, which is the image distance from the mirror, and that's going to be 53 centimeters. Now here's M. 53 over 93 So it'll be real inverted image. Let's review. So there is the focal length. This is the distance from the mirror the object is. That's the distance from the mirror the image is. That's the magnification. It's going to be the real image, and it's going to be an inverted image. And here are the ray diagrams to support the calculations. And it's just going to keep on going until it's finished. Just check your work. All right, that's it. That's all the information. A concave makeup mirror is designed so that a person 25 centimeters in front of it sees an upright image at a distance of 50 centimeters behind the mirror. What is the radius of curvature of the mirror? What is the magnification of the image? Is the image real or virtual? Here's P and Q, and I certainly hope the image is virtual. Otherwise, why would it be useful as a mirror? So here are the calculations. We'll just let that go. The radius of curvature is 100 centimeters. So that's about a meter radius. So it's a 2 meter, if you think of a 2 meter wide sphere, it's a pretty big mirror. So the magnification will be 2 times, and it's going to be a virtual image. And it'll be twice the size. So now we're going to review, put all the data together, see what we have. There's P and Q, radius of curvature, just let this run. M is 2, again, and you see where it is. You see that it's virtual and that it's upright. Otherwise, it would be difficult to apply makeup if your image is upside down. And so it's going to be a virtual upright image. A pen placed 11 centimeters from a concave spherical mirror produces a real image 13.2 centimeters from the mirror. What is the focal length of the mirror? What is the magnification of the image? If the pen is placed 27 centimeters in front from the mirror, what is the new position of the image? What is the magnification of the new image? Is the image real or virtual? Draw ray diagrams to confirm your results. So ponder that for a moment and then get your information together. I'll just let that run. Okay, where are we? All right. So we have the second magnification, which is about a third, 0.285, a little less than a third. So there's all the information. Put everything together nicely. There's scenario 1 and scenario 2. And there's the diagram. And there's the second diagram, all nicely put together. Convex spherical mirrors. On recent models of automobiles, there is a side view mirror on the passenger side of the car, unlike the flat mirror on the driver's side, which produces unmagnified images. The passenger's mirror bulges outward at the center. Images in this mirror are distorted near the mirror's edge, and the image is smaller than the object. This type of mirror is called a convex spherical mirror. Convex spherical mirror, a mirror whose reflecting surface is an outward curved segment of a sphere. Sort of like the opposite of the concave mirror. Here is the table 5, sign conventions for mirrors. Study it very carefully, and you're going to be using it a lot. These are the sign conventions when things are positive and negative, etc. Here's table 5, visual strategy. Make sure that students properly interpret information related to all the cases listed in table 5. Point out that as a good general rule, distances in front of the mirror are assigned a positive sign, and distances behind the mirror are assigned a negative sign. So study the table before we begin. Question 1. The image formed by a mirror, a concave mirror, is upright and virtual. What would be the signs of R, F, Q, and H? So it would be a positive R, it would be a positive F, it would be a negative Q, and it will be a positive H prime. Question 2. The image formed by a convex mirror is also upright and virtual. What would be the signs of R, F, Q, and H prime? Think. Let's see. R would be negative. F would be negative. Q would be negative. And H prime would be positive. A convex spherical mirror is a segment of a sphere that is silvered so that light is reflected from the sphere's outer convex surface. This type of mirror is also called a diverging mirror because the incoming rays diverge after reflection as though they were coming from some point behind the mirror. The resulting image is therefore always virtual, and the image distance is always negative. Because the mirrored surface is on the side opposite the radius of curvature, the convex spherical mirror also has a negative focal length. The sign conventions for all mirrors are summarized in Table 5. The technique for drawing ray diagrams for a convex mirror differs slightly from those of a concave mirror. Light rays diverge upon reflection from a convex mirror, A, forming a virtual image that is always smaller than the object, B. Study the diagram carefully. All of the answers really are approximately the same for convex mirrors. The focal point and center of curvature are situated behind the mirror's surface. Dotted lines are extended along the reflected reference rays to points behind the mirror as shown in figure 13a. A virtual upright mirror forms where the three rays apparently intersect. Magnification for convex mirrors is always less than 1, as shown in figure 13b. Convex spherical mirrors take the objects in a large field of view and produce a small image, so they are well suited for providing a fixed observer with a complete view of a large area. Convex mirrors are often placed in stores to help employees monitor customers and at the intersections of busy hallways so that people in both hallways can tell when others are approaching. They're also big in parking garages and around tight corners. The side view mirror of the passenger side of a car is another application of the convex mirror. The mirror usually carries the warning objects are closer than they appear. Without this warning, a driver might think that he or she is looking into a flat mirror, which does not alter the size of the image. The driver could therefore be fooled into believing that a vehicle is farther away than it is because the image is smaller than the actual object. There are certain circumstances in which the object for one mirror is the image that appears behind another mirror. In these cases, the object is virtual and has a negative object distance. Because of the rarity of these situations, virtual object distances p is less than 0 has not been listed in Table 5. An upright pencil is placed in front of a convex spherical mirror at a focal length of 8 centimeters. An erect image of 2.5 centimeters tall is formed 4.44 centimeters behind the mirror. Find the position of the object, the magnification of the image, and the height of the pencil. All right, again, here are the rules. I'm just going to let this play 4 seconds per slide. Get what you can, put it on pause when you need it. Because the mirror is convex, the focal length is negative. The image is behind the mirror, so Q is also negative. All right, here are some more givens. You want to construct a ray diagram. There it is. Choose an equation or situation. Use the mirror equation. Remember what you're looking for. That's important. Use the magnification equation. Choose an equation or situation. Use the mirror equation. You're going to rearrange the values. Just let things go here. Here's the equations. Here's what's given. So you're looking for P. That's one thing you're looking for. So P is 10 centimeters. That means it's in front of the mirror. H is going to be positive as well. H is positive. So it's going to be a positive 5.63. That's the object. And the magnification is going to also be positive. It's going to be upright. It's going to be 0.444, so that'll be smaller than the actual image. Here is the diagram with the various values in them. All right. Number 1, the image of a crayon appears to be negative 23 centimeters behind the surface of a convex mirror and is upright plus 1.7 centimeters tall. If the mirror's focal length is negative 46 centimeters, how far in front of the mirror is the crayon position? What is the magnification of the image? Is the image virtual or real? Is the image inverted or upright? How tall is the actual crayon? Okay, here's the mirror equation. Here is what is given. And those are the 4 things that we want to do. How far in front of the mirror is the crayon positioned? What is the magnification of the image? Is the image virtual or real? Is the image inverted or upright? How tall is the actual crayon? So I kind of summarized what the questions were. All right, there's the modified mirror equation. And now let's find M. M is going to definitely be positive, virtual, upright image. It's going to be half the size. Now the H. We know what H prime is. We know what the magnification is. So it's going to be a 3.40 centimeter object, virtual upright image. Okay, so here are the questions. Let's put everything together now. So plus 46 is P, plus 0.5 is M. It's virtual. It's upright. And the actual crayon object is 3.4 centimeters. Here are the values put on a diagram. Okay, next problem. A concave mirror with a focal length of 0.25 meters forms a 0.080 meter tall image of an automobile at a distance of 0.24 meters behind the mirror. What is the magnification of the image? Where is the car located? And what is its height? Is the image real or virtual? Is the image upright or inverted? Okay, so here are the values, the given. Here's the equation. We're going to solve for P. Should be getting to be an old pro at this by now. P is 6 meters. And now what? Now we're going to solve for M. I'll just let this roll. All right, now H. Plug in the values. And you have 2 meters. All right, let's summarize everything, make sure we got this. So M is 0.04. 6 meters is the distance in front of the mirror. It's going to be a virtual image because it's a convex lens, convex mirror, and it's going to be upright. And there you have it again. Here are the values being fitted into the diagram. Okay, next. A convex mirror of focal length 33 centimeters forms an image of a soda bottle at a distance of 19 centimeters behind the mirror. If the height of the image is 7 centimeters, where is the object located and how tall is it? What is the magnification of the image? Is the image virtual or real? Is the image inverted or upright? Draw a ray diagram to confirm your results. There are the givens. There's the equation. Plug in. And P equals 45 centimeters. Now we have P there, it's 45 centimeters. Now what we're going to do, we need H. We have enough to plug in for H. And it looks like it's going to be positive. So it's going to be upright, 17 centimeters tall. Now do the magnification. And you see that it's going to be smaller than the original. The image is going to be small, 0.41. And here is the summary. Make sure we have everything. And this is the diagram. And the next one. A convex mirror with a radius of curvature of 0.550 meters is placed above the aisle in a store. Determine the image distance and magnification of a customer lying on the floor 3.1 meters below the mirror. Is the image virtual or real? Is the image inverted or upright? You'll never know I'm here. I'm just going to kind of like let things roll by themselves. See if you can do this, put it on pause, stop, and then check your final answer. Okay, a spherical glass ornament is 6 centimeters in diameter. If an object is placed 10.5 centimeters away from the ornament, where will its image form? What is the magnification? Is the image virtual or real? Is the image inverted or upright? Again, this should become second nature to you after a while, just in sheer repetition. So here's what's given. And there's the equation I'm going to use. And that's where I'm going to plug in. And that's going to calculate negative 1.31 meters. There's the given. Now we're going to do M. .125, so it'll be a small image, virtual and upright. Here is the summary. Virtual, and it'll be upright. Okay, next. A candle is 49 centimeters in front of a convex spherical mirror that has a focal length of 35 centimeters. What are the image distance and magnification? Is the image virtual or real? Is the image inverted or upright? Draw a ray diagram to confirm your results. That's what's given. There's the equation. I'm going to plug into the equation. And I'm going to calculate. Q is negative 20 centimeters. And this is M. Plug in for M. negative 20 centimeters. I don't have that written on the side there, but I'll put that in. I'll change it. So it's going to be virtual upright image. And let's put things in here. And upright, virtual and upright. There is the ray diagram. Figure 14, spherical aberration occurs when parallel rays far from the principal axis converge away from the mirror's focal point. Sounds like what might have been the problem with the Hubble telescope. Here's figure 14, visual strategy. Remind students that for a spherical mirror, the normal to the surface at any point lies along the radius at that point. Point out that each pair of reflected rays at equal distances on opposite sides of the principal axis cross one another on the principal axis. Question 1. How does the angle of incident vary when the incoming ray is farther away from the principal axis of a spherical mirror? Mark the points where each pair of reflected rays intersect. Where will the next pair intersect if the mirror's surface is extended? Answer. The angle of incident increases. The points should be marked on the principal axis to the right of F. The points of intersection come closer to the mirror's surface and the focal point becomes more ill-defined. You're going to want to read that over, make sure that makes sense. Parabolic mirrors. You have probably noticed that certain rays in ray diagrams do not intersect exactly at the image point. This occurs especially with rays that reflect at the mirror's surface far from the principal axis. The situation also occurs with real light rays and real spherical mirrors. If light rays from an object are near the principal axis, all of the reflected rays pass through the image point. Rays that reflect at points on the mirror far from the principal axis converge at slightly different points on the principal axis as shown in figure 14. This produces a blurred image. This effect, called spherical aberration, is present to some extent in any spherical mirror. Parabolic mirrors eliminate spherical aberration. A simple way to reduce the effect of spherical aberration is to use a mirror with a smaller diameter. That way, the rays are never far from the principal axis. If the mirror is large to begin with, shielding its outer portion will limit how much of the mirror is used and thus will accomplish the same effect. However, many concave mirrors, such as those used in astronomical telescopes, are made large so that they will collect a large amount of light. An alternative approach is to use a mirror that is not a segment of a sphere, but still focuses light rays in the manner similar to a small spherical concave mirror. This is accomplished with a parabolic mirror. Figure 15, all parallel rays converge at a parabolic mirror's focal point. The curvature in this figure is much greater than it is in real parabolic mirrors. Parabolic mirrors are segments of a paraboloid, a three-dimensional parabola, say that 3 times fast, whose inner surface is reflecting. All rays parallel to the principal axis converge at the focal point regardless of where on the mirror's surface the rays reflect. Thus, a real image forms without spherical aberration, as illustrated in figure 15. Similarly, light rays from an object at the focal point of a parabolic mirror will be reflected from the mirror in parallel rays. Parabolic reflectors are ideal for flashlights and automobile headlights. Spherical mirrors are extensively used because they are easier to manufacture than parabolic mirrors and are thus less expensive. Reflecting telescopes use parabolic mirrors. A telescope permits you to view distant objects, whether they are building a few kilometers away or galaxies that are millions of light years from Earth. Not all telescopes are intended for visible light. Because all electromagnetic radiation obeys the laws of reflection, parabolic surfaces can be constructed to reflect and focus electromagnetic radiation of different wavelengths. For instance, a radio telescope consists of a large metal parabolic surface that reflects radio waves in order to receive radio signals from objects in space. There are two types of telescopes that use visible light. One type is called a refracting scope that uses a combination of lenses to form an image. The other kind uses a curved mirror and small lenses to form an image. This type of telescope is called a reflecting telescope. Students may be unclear about the difference between segments of a circular and a parabolic curve. Ask them to draw the continuation of a circular and parabolic curves of the mirrors to see that the curves are similar for a short segment. Have students compare the curves of a circular and parabola by using their graphing calculators to compare the curves whose equations are y equals the square root of 1 minus x squared and y equals negative x squared. Figure 16, the parabolic objective mirror in a Cassegrain reflector focuses incoming light. Reflecting telescopes employ a parabolic mirror called an objective mirror to focus light. One type of reflecting telescope called a Cassegrain reflector is shown in figure 16. Parallel light rays pass down the barrel of the telescope and are reflected by the parabolic objective mirror at the telescope's base. These rays converge toward the objective mirror's focal point F, where a real image would normally form. However, a small curved mirror that lies in the path of the light rays reflect the light back towards the center of the objective mirror. The light then passes through a small hole in the center of the objective mirror and comes to a focus at point A. An eyepiece near point A magnifies the image. You may wonder how a hole can be placed in the objective mirror without affecting the final image formed by the telescope. Each part of the mirror's surface reflects light from distant objects, so a complete image is always formed. The presence of the hole merely reduces the amount of light that is reflected. Even that is not severely affected by the hole because the light gathering capacity of the objective mirror is dependent on the mirror's area. For instance, a 1 meter diameter hole in a mirror that is 4 meters in diameter reduces the mirror's reflecting surface by only 1/16 or 6.25%. Section review. A steel ball bearing with a radius of 1.5 centimeters forms an image on an object that has been placed 1.1 centimeters away from the bearing surface. Determine the image distance and magnification. Is the image virtual or real? Is the image inverted or upright? Draw a ray diagram to confirm your results. This is the radius of curvature and the P. Here's the equation, including the radius of curvature. Plug in the data, including your signs, and you get negative 0.45 centimeters. Here's M. I'm just going to let this run. I think you're going to be pretty good at this now. 0.41, so it's going to be smaller. And it's going to be virtual, and it will be upright. And here's a review of everything. And here it is on a diagram. A spherical mirror is to be used in a motion picture projector to form an inverted real image 95 times as tall as the picture in the single frame of film. The image is projected on screen 13 meters from the mirror. What type of mirror is required, and how far should it be from the film? I'll just let things run. So notice that M is negative 95. And here is the answer, the diagram. This is from table 4, number 4, and all of the values are written in. So it should be fairly clear. Study it carefully. Which of the following images are real and which are virtual? A, the image of a distant illuminated building projected onto a piece of heavy white cardboard by a small reflecting telescope. B, the image of an automobile in a flat rearview mirror. And C, the image of shop aisles in a convex observation mirror. A is going to be real. B is inside the mirror, so that'll be virtual. And C, you can also see inside the mirror, so that will be virtual. Why is the image formed by a parabolic mirror sharper than the image of the same object formed by a concave spherical mirror? Think. We did it almost near the end of that section. And the rays reflected by a parabolic mirror all focus at one point, whereas the rays reflected by a concave spherical mirror reflect along a line that includes the mirror's focal points. The reflector of the radio telescope at Arecibo has a radius of curvature of 265 meters. How far above the reflector must the radio detecting equipment be placed in order to obtain clear radio images? Think. Capital R is 265. And what is going to be the relationship? What is the name of the place where you're going to put the collecting equipment? P is infinite, because you're collecting stuff from outer space. 1 over P approaches 0. Therefore, 1 over Q equals 2 over R. And so, it's going to be half, 132.5 meters, which is the telescope's focal length, 132.5 meters. Here is a picture to help along with that. It's a bit of a visual. Okay. Section 4, color and polarization. Recognize how additive colors affect the color of light. Recognize how pigments affect the color of reflected light, and explain how linearly polarized light is formed and detected. Color. You have probably noticed that the color of an object can appear different under different lighting conditions. These differences are due to differences in the reflecting and light absorbing properties of the object being illuminated. So far we have assumed that objects are either like mirrors, which reflect almost all light uniformly, or like rough objects, which reflect light diffusely in several directions. But, as mentioned in section 1, objects absorb certain wavelengths from the light striking them and reflect the rest. The color of an object depends on which wavelengths of light shine on the object and which wavelengths are reflected. See figure 17. You can go back and see figure 17. I think actually that's going to be next, figure 17. Here's figure 17. The leaf appears green because it's reflecting the green light and absorbs others. If all wavelengths of incoming light are completely reflected by an object, that object appears to have the same color as the light illuminating it. This gives the object the same appearance as a white object illuminated by the light. An object of a particular color, such as the green leaf in figure 17, absorbs light of all colors except the light whose color is the same as the object's color. By contrast, an object that reflects no light appears black. In truth, leaves appear green only when their primary pigment, chlorophyll, is present. In the autumn, when the green pigment is destroyed, other colors are reflected by the light. At night, what color is reflected? That's a question. Additive primary colors produce white light when combined. Because white light can be dispersed into its elementary colors, it is reasonable to suppose that elementary colors can be combined to form white light. One way of doing this is to use a lens to recombine light that has been dispersed by a prism. Another way is to combine light that has been passed through red, green, and blue filters. This light, these colors are called the additive primary colors because when they are added in varying proportions, they can form all the colors of the spectrum. Here's table 6, additive and subtractive primary colors. Look at the chart carefully. You'll see that the additive colors are red, green, and blue. Those are the primary. And the cyan, magenta, and yellow are the subtractive colors, meaning they're the primary of the subtractive colors. So study this carefully. You'll get it. And this particular chart is very good for the additive. The combination of additive primary colors in any two circles produce the complementary color of the third additive primary color. So you can see that blue and red is magenta, and green and red is yellow, etc. When light passed through a red filter is combined with green light produced with a green filter, a patch of yellow light appears. If this yellow light is combined with blue light, the resulting light will be colorless or white, as shown in figure 18. Because yellow is the color added to the primary additive color blue to produce white light, yellow is called the complementary color of blue. Two primary colors combine to produce the complement of the third primary color, as indicated in Table 6. One application of additive primary colors is the use of certain chemical compounds to give color to glass. Iron compounds give glass a green color. Manganese compounds give glass a magenta or reddish blue color. The brightness of the red, green, and blue pixels of a color television screen are adjusted such that from a distance all of the colors in a single picture appear. If you take a piece of magazine, like a picture from a magazine, and put it under a microscope, you'll see the subtractive colors that will make up pigments, and you subtract them: magenta, yellow, and cyan. Very similar to the ink in a color printer. Green and magenta are complementary colors, so the right proportions of these compounds produce an equal combination of green and magenta light, and the resulting glass appears colorless. Another example of additive colors is the image produced on a color television screen. A television screen consists of small luminous dots or pixels that glow either red, green, or blue when they are struck by electrons. See figure 19. Varying the brightness of different pixels in different parts of the picture produce a picture that appears to have many colors present at the same time. Humans can see in colors because there are three kinds of color receptors in the eye. Each receptor, called a cone cell, is sensitive to either red, green, or blue light. Lights of different wavelengths stimulate a combination of these receptors so that a wide range of colors can be perceived. Subtractive primary colors filter out all light when combined. When blue light and yellow light are mixed, white light results. However, if you mix a blue pigment, such as paint or the colored wax of a crayon, with yellow pigment, the resulting color is green, not white. This difference is due to the fact that pigments rely on colors of light that are absorbed or subtracted from the incoming light. For example, yellow pigment subtracts yellow and violet colors from white light and reflects red, orange, yellow, and green light. Blue pigment subtracts red, orange, and yellow from the light and reflects green, blue, and violet. When yellow and blue pigments are combined, only green light is reflected. This chart may help. Figure 20, the combination of the subtractive primary colors by any two filters produces the complementary color of the third subtractive primary color. When pigments are mixed, each one subtracts certain colors from white light, and the resulting color depends on the frequencies that are not absorbed. The primary pigments, or primary subtractive colors, as they are sometimes called, are cyan, magenta, and yellow. These are the same colors that are complementary to the additive primary colors. See Table 6. When any two primary subtractive colors are combined, they produce either red, green, or blue pigments. When the three primary pigments are mixed together in proper proportions, all of the colors are subtracted from white light and the mixture is black, as shown in figure 20. Combining yellow pigment and its complementary color, blue, should produce a black pigment. Why don't you look back at figure 20 and see if that makes any sense to you whatsoever. Yet earlier, blue and yellow were combined to produce green. The difference between these two situations is explained by the broad use of color names. The blue pigment that is added to a yellow pigment to produce green is not a pure blue. If it were, only blue light would be reflected from it. Similarly, a pure yellow pigment will reflect only yellow light. Because most pigments found in paints and dyes are combinations of different substances, they reflect light from nearby parts of the visible spectrum. Without knowledge of the light absorption characteristic of these pigments, it is hard to predict exactly what colors will result from different combinations. Again, look back at the figures for this, figure 20 specifically. Colors in a blanket brown is a mixture of yellow with small amounts of red and green. If you shine a red light on a brown woolen blanket, what color will the blanket appear? Will it appear lighter or darker than it would under white light? Blueprints. If a blueprint, a blue drawing on a white background, is viewed under blue light, would you still be able to perceive the drawing? What will the blueprint look like under yellow light? The answer, number one, red, darker. Some of the red light is absorbed by the green pigment. Assume that yellow pigment consists of green and red pigments. Blueprints. No, the entire page will look blue. The blueprint may appear darker depending on the light source. The blue drawing will become black and the page will be yellow. Each side of the triangle is the complementary color of the color at the opposite vertex. This diagram also shows the results of combining pigments. The colors at any two sides of the triangle combine to form the color at the vertex between them. For example, pure magenta pigment mixed with pure cyan pigment will only reflect blue light. The pigment whose name is on one side reflects the light composed of the colors that are indicated at the vertices on either end of that side. This same pigment absorbs the light with the color whose name is on the opposite vertex. Figure 21, randomly oscillating electric fields produce unpolarized light. Study that carefully, and let's continue. Polarization of light waves. You have probably seen sunglasses with polarized lenses that reduce glare without blocking the light entirely. There is a property of light that allows some of the light to be filtered by certain materials in the lenses. In an electromagnetic wave, the electric field is at right angles to both the magnetic field and the direction of propagation. Light from a typical source consists of waves that have electric fields oscillating in random directions, as shown in figure 21. Light of this sort is said to be unpolarized. Electric field oscillations of unpolarized light waves can be treated as combinations of vertical and horizontal electric field oscillations. Look back at the former slide and see if that makes any sense. Here is figure 22. Light waves with aligned electric fields are linearly polarized, as opposed to 21 where it was not polarized. There are certain processes that separate waves with electric field oscillations in the vertical direction from those in the horizontal directions, producing a beam of light with electric field waves oriented in the same direction, as shown in figure 22. These waves are said to have linear polarization. Linear polarization, the alignment of electromagnetic waves in such a way that the vibrations of the electric fields in each of the waves are parallel to each other. Light can be linearly polarized through transmission. Certain transparent crystals cause unpolarized light that passes through them to become linearly polarized. The direction in which the electric fields are polarized is determined by the arrangement of the atoms or molecules in the crystal. Light will pass through a pair of polarizing films with their polarization axes are aligned in the same direction. When the axes are at right angles to one another, light will not get through. For substances that polarize light by transmission, the line along which light is polarized is called the transmission axis of the substance. Only light waves that are linearly polarized with respect to the transmission axis of the polarizing substance can pass freely through the substance. All light that is polarized at an angle of 90 degrees to the transmission axis does not pass through. When two polarizing films are held with the transmission axis parallel, light will pass through the films, as shown in figure 23a. If they are held with the transmission axis perpendicular to each other, as in figure 23b, no light will pass through the films. A polarizing substance can be used not only to linearly polarize light, but also to determine if and how light is linearly polarized. Figure 24. The brightness of the polarized light decreases as the angle increases between the transmission axis of the second polarizer and the plane of polarization of light. By rotating a polarizing substance as a beam of polarized light passes through it, a change in the intensity of the light can be seen. See figure 24. The light is brightest when its plane of polarization is parallel to the transmission axis. The larger the angle is between the electric field waves and the transmission axis, the smaller the component of light that passes through the polarizer will be, and the less bright the light will be. When the transmission axis is perpendicular to the plane of polarization for the light, no light passes through. Figure 25, at a particular angle, reflected light is polarized horizontally. This light can be blocked by aligning the transmission axis of the sunglasses vertically. Light can be polarized by reflection and scattering. When light is reflected at certain angles from a surface, the reflected light is completely polarized parallel to the reflecting surface. If the surface is parallel to the ground, the light is polarized horizontally. This is the case with glaring light that reflects at a low angle from roads, bodies of water, and car hoods. Because the light that causes glare is in most cases horizontally polarized, it can be filtered out by a polarizing substance whose transmission axis is oriented vertically. This is the case with polarizing sunglasses, as shown in figure 25. The angle between the polarized reflected light and the transmission axis of the polarizer is 90 degrees. Figure 26, the sunlight scattered by air molecules is polarized for an observer on Earth's surface. Thus, none of the polarized light passes through. In addition to reflection and absorption, scattering can also polarize light. Scattering, or the absorption and re-radiation of light by particles in the atmosphere, causes sunlight to be polarized, as shown in figure 26. When an unpolarized beam of sunlight strikes air molecules, the electrons in the molecules begin vibrating with the electric field of the incoming wave. A horizontally polarized wave is emitted by the electrons as a result of their horizontal motion, and a vertically polarized wave is emitted parallel to Earth as a result of their vertical motion. Thus, an observer with his or her back to the sun will see polarized light when looking up toward the sky. Section review number 1. A lens for a spotlight is coated so that it does not transmit yellow light. If the light source is white, what color is the spotlight? It must be blue. A house is painted with pigments that reflect red and blue light, but absorb all others. What color does the house appear to be when it is illuminated by white light? What color does it appear to be under red light? Well, it would be magenta and it would be red. What primary pigments would an artist need to mix to obtain a pale yellow-green color? What primary additive colors would a theater lighting designer need to mix in order to produce the same color with light? So if you can get this, you really are on your way. It says, what primary pigments would an artist need to mix to obtain a pale yellow-green color? What primary additive colors would a theater lighting designer need to mix in order to produce the same color? So the first one is going to be subtractive to get the pale yellow-green, and the next one is going to be what colors do you add? So it's actually, you're kind of going for a cyan-like color. So yellow and cyan, more yellow than cyan because it's that pale color, but cyan is pretty good. And the next one is going to be green and red, mostly more green than red, because green and red does make cyan in terms of the colors. The light reflected from the surface of a pool of water is observed through a polarizer. How can you tell if the reflected light is polarized? How can you tell? If you turn the polarizer and very little light is transmitted, then the reflected light is polarized. All right, now let's look at the key ideas from each section. And we have section 1. Light is electromagnetic radiation that consists of oscillating electric and magnetic fields with different wavelengths. The frequency times the wavelength of electromagnetic radiation is equal to c, the speed of light. The brightness of light is inversely proportional to the square of the distance from the light source. Let's look at section 2. Flat mirrors. Light obeys the law of reflection, which states that the incident and reflected angles of light are equal. Flat mirrors form virtual images that are the same distance from the mirror's surface as the object is. Section 3, curved mirrors. The mirror equation relates object distance, image distance, and focal length of a spherical mirror. The magnification equation relates image height or distance to object height or distance, respectively. Let's look at section 4, color and polarization. Light of different colors can be produced by adding light consisting of primary additive colors, red, green, and blue. Pigments can be produced by combining subtractive colors, magenta, yellow, and cyan. Light can be linearly polarized by transmission, reflection, or scattering. And this ends the chapter on reflection of light.